going to experience some time together now with Mod 1, which is how the brain learns math. We're going to ground ourselves in an essential question for this module. And to be, what do I want to say? Like to draw some inspiration from the brilliance of the students in our district, we're going to start by looking at an essential question routine that a teacher, Ms. Eason, does with 6th grade students to ground their thinking about the math they're going to be learning for the week. So they start off on day 1 with what is the essential question? And then they write down their first initial thoughts. It's just a 2 or 3 minute routine. Then they learn some things together. The next day they come in and they add to their essential question. They do that throughout the week. And you can see some things evolving here. Their essential question is, what real life situations can be modeled by 3C plus 5? This student says it could mean 3 cookies plus 5 cookies and has a picture here. They learn some things. They come back the next day. They continue to evolve. What's really cool about this is later on in the week, the student came up and identified that was wrong. But they didn't erase it. They didn't hide it. They didn't feel any sort of embarrassment. It was just part of the learning of this essential question for the week. Right here, they identified, oh, even in this section, I did not know. We have to not know to be able to learn. So an essential question routine like this allows students to make their thinking visible, authentically live writing in mathematics as they're continuing to evolve and learn and grow. And then they get into warning. This is shown for educational only. Never house hamsters together. There's some humor that gets evolved, and you can hear them as you are experiencing their essential question evolution. I'm going to ask us to embrace this and take some risks in this module. We will have an essential question. We'll put some initial thoughts down. We'll come back. We'll learn some things. We'll evolve and continue to go. Here's another one. The student, the very first sentence is, I really don't understand what this is. Great. It's okay to not know, because I have to not know to be able to learn. So in math, sometimes we're not as good at normalizing not knowing, and we set up an environment of what's the answer, and raise your hand to tell the answer or talk about the answer. And so normalizing the learning process allows us to center taking the risk and being confident and saying, I don't know yet. I'm not sure about this, but I'm ready to learn. Then they continue to build on, talk about what they think C is and the coefficient and so on. And this picture is a picture of a brain with a like barbell, so like strength. And it says my brain's languages. And it's super small, but it says Inglés, Español, and algebra. So recognizing that my brain is powerful and it thinks and communicates in 3 languages. So you are going to be inspired by those 6th grade students. And this is our first essential question. How does the brain learn math? And just like Ms. Eason and her students do, we're going to come back to this throughout our section of this essential question. So you'll have an opportunity to reflect, think, and add, and revise, and write notes to yourself and arrows as we move on. The beautiful thing, by the end of this week, you can see the academic language starting to build. You can literally see live and in action the building of the learning that's happened throughout the week in the students' own words, to the point that they built an accurate representation of 3C plus 5 in real world terms that connected to the student. What do you see in this picture? Hold it in your head right now. What do you see in this picture? This is a picture of a telephone. It's all of those other things that we saw too. My learning goal and reason for putting this in here is because I want us to think about phones when they were first a thing. What did phones look like when your parents were kids? What did they look like when you were a kid? What did they look like when you were in high school? 5 years ago? Today? They don't look the same. Why? So society has evolved, so the tools that we need have evolved, and therefore things that we once had that served a purpose then may no longer serve a purpose in society right now, so they continue to evolve. Think about the evolution of phones. In the last 20 years, they've evolved dramatically, right? Because of advancements in technology. Those same advancements in technology allow us to literally take pictures of students' brains when they are constructing new knowledge. That's something we couldn't do 15 years ago. So a lot of the things that we'll talk about today are based on those advancements in technology and being able to see what's going on in students' brains and understanding that, oh, that's what's happening, and this is what we need to do to orient their brain to that part of the brain. And know that research from neuroscience and cognitive science takes anywhere from 10 to 20 years to make it into practitioners' field. So, advancements in technology. Things have evolved and society has evolved. When we think about learning math, there's been some evolution, but not as dramatic as technology has allowed us to evolve it, and not as dramatic as societal needs have evolved for what our math students need to be experiencing and doing. Another interactive. If we're at the point where you can close your eyes, our trust level is there, feel free to do that. If you want to keep them open, that's fine too. But I'm going to ask you to pay attention to what happens in your body whenever I say a word. Okay? Water. Elephant. Subluxation. Division of fractions. When I know a concept, when I own it, I have a picture I can recall. I have a sensory response that I can recall. I can remember moving my body. I can pull up a mental image, but I have some way of recalling this. If I don't own it, I pull up just the word. I don't have meaning behind it. I don't have a picture behind it. It's just the word, or it's just a black screen or a white screen or nothingness there. So when I own mathematical concepts, I have a way of recalling them through my senses, usually through pictures. People will say I'm a visual learner, I need to see it. There is no research that proves learning modalities, a visual, kinesthetic, auditory. Actually, we need to experience learning with all of our senses. And especially in math, we need to experience that pictorial phase of learning so that we can make pictures of it. Okay? Division of fractions. So we'll go there for a minute. You don't have to share this one out, but think, what do you see when I say division of fractions? Do you have a picture of models that can do it? Do you have numbers and symbols with a copy dot flip or a trick to remember how to get the answer? That was me. I knew how to get the answer, but I didn't have a picture for it. And my BS is in math. So I had an identity of being a strong math student. I started teaching 5th grade math. That was my first job. And I thought that I really understood mathematics. And then I started teaching and I went, oh, I understand the procedures and how to get answers, but I don't understand the why. And a little bit later, we'll talk about why that worked okay for me and maybe some that are in a similar generational experience, but why it doesn't now because of the society and the rules that our kiddos are playing by that are different. I also, when I started teaching pre-service teachers, when we got to the section of division of fractions, I literally said, don't worry about the pictures. It takes too much time. They're confusing anyways. Skip them. Just do the copy dot flip because you can get an answer quicker and you got too much to do, especially as elementary teachers. So just skip that part and help them get this. I realized once I started learning about how the brain learns math and pictures in my grad program that I was saying, I don't understand the picture. I don't understand how division of fractions works with models. And that's okay. We need to normalize as professional educators and promoters of learning that we don't know everything. And it's okay for us in our times, in our collaborative times, to sit together and muck through it and check ourselves. Anytime we're asking students to learn something, ask ourselves, what's the picture? Do we know the picture? And if not, let's spend some time developing that picture together. Then we can talk about how we help students develop the picture. Okay? So, if I have water, conceptually, it lives back here in my brain. I have a picture for it, a recall of it. Subluxation, I can tell you what the definition is of it, and that would put it right here. To have it here, you'd have to have a picture and experience with it. It's not a math term, by the way. Does anybody know what it is? Yeah, it's a chiropractic term. It means whenever you say my back's out or have something out, you have a subluxation. Division of fractions, you can do a check. Where is it right now for you? Do you have the conceptual pictures for it and the models and can explain the why when I divide two fractions, I get a bigger number, but when I divide whole numbers, I don't? What's happening there? About that. But we're going to do a brief intro to the brain and how it works because we're professional promoters of learning. We spend a lot of time talking about teaching and how to teach. We need to spend more time talking about learning and how learning happens. So then we know what we're doing is in support of learning or not. Okay? So in the brain, oh, it's working. This little blue ridge here, there's 3 letters by it. It's called the IPS. It's going to be a Trivial Pursuit question someday. I'm convinced of it. And you will learn, you will win with it. That's the region where conceptual math learning lives. That's why I always point back here when I'm talking about I have a conceptual understanding. The intraparietal sulcus. It exists in both hemispheres. That's also a myth, that you're a left brain or a right brain, and that supports whether you're a math learner, a strong math learner or not. The IPS is actually in the connection of both hemispheres. And so whenever we are constructing conceptual math knowledge, it's building those highways for which all other information travels, including language acquisition, communication, and reading comprehension. So we may segment the math part of our day and the literacy part of our day as separate parts of learning, but when we are engaging students in conceptual math learning back here, we are actually supporting them as multilingual learners, as stronger communicators, critical thinkers, and reading comprehension and writing improves as well. Have you ever crammed for a test? Or someone tells you a phone number or a password and you repeat it over and over and over again so you don't forget it? You're accessing this part of your brain when you're doing that. That's the memorization part of your brain, and it's short term. In the memorization part of our brain, we can only hold so much. It's like whenever you have a tab open on your computer, and then you open another tab and another tab and another tab, and eventually there's so many tabs open, what do? I just got to close it, just got to shut down, right? That happens in this part of our brain too. And if we're experiencing math in a way where our teacher is going to this part of our brain, which is how many of us may have experienced math, and that is in an I do, we do, you do model. So I'm going to show you how to do it. You're going to do what I showed you, and then you're going to practice it independently. That helps go to this part of the brain, which works for memorization and short-term information. But I can only hold so much here. And this is why students will cap out and cliff out at a certain point. It is either I liked math until 3rd grade, I liked math until fractions, I liked math until algebra, or I liked math until calculus. Because I can only hold so much here before my brain's like, can't do it anymore, and now it's not making sense to me because I can't access it from back here. The other thing that's really important to remember for this part of the brain is if I'm experiencing chronic or acute stress or trauma, this is the part of my brain that gets shut down. Cortisol dumps here, shuts down, and all these functions remain. So test anxiety, it's a true thing. Math anxiety, true thing. Part of my brain that experiences pain is the same part of my brain that lights up if I'm experiencing math anxiety or trauma. It's physiologically painful for some students if they are not allowed to think through back here. But just like all traumas, we can heal from it, right? So if I'm experiencing chronic or acute stress or trauma, my teacher is doing their very best to help me learn math by putting it here, but it's shut off because of these other things. Or if I have a true diagnosed learning difference, this is the part that's shut off also. That is when we're like, I'm doing all these things and it's just not sticking. I'm not sure what else to do. It may mean that we are orienting to this part of their brain instead of back here. So how do we stay back here? Sensory motor, it's connected to the sensory motor. I know PE is in here, and art is in here, and music is in here, and some of our other specials, I believe. Sensory motor is the part that moves our body and knows where we are in space. It's really important to move in support of math learning. Using things like Legos and building and blocks and physically moving objects, including my body, in space is growing the part of my brain that thinks mathematically. Remember those cliff points that I said? There are students that make it all the way through K-12, have a desire to become engineers, and get admitted to universities as engineering majors. So think about what you would assume of their math and science learning experiences and abilities. Those students that enter at the university as engineering majors, 39% of them will change majors the first year because of math and their visual spatial reasoning. So whenever I'm having students build with blocks and move things around, that's in support of their math brain. It's connected to that sensory motor. Of those engineering majors that begin, only 60%. We'll finish. So that we may have the success short term, and it may work for this unit. It may work for this grade, but eventually, if we aren't helping students develop the math here, they're going to cap out. This is some of the research that the things I just spoke about are from. There's a lot of details in there, but I want you to pay attention to the dates. Right? So we're constantly learning new things, just like our phones are constantly being upgraded and new. And so part of our learning today is to be, what do we most currently know, and what resonates with me that I can take that I'm going to really focus on evolving in my practice that's in support. When students are engaging their IPS, these are some things that we will see them doing. If they are up and at the board and changing the plane, so if I'm working on this plane versus writing up here, it flips and connects to a different part of the brain. So if you can get them up and moving and writing on the wall, that can be helpful. This picture is my favorite. What do you notice she's doing? Yeah. She's literally holding the part of her brain that is growing mathematical knowledge live and in that moment. It's tiring whenever I am growing mathematical information here. And then their eyes. What do you notice about their eyes? Yeah. When they're looking up and in that direction, they're either trying to retrieve something from the IPS or put something in the IPS. So some checks that I can do with my students and myself, we talk about wait time a lot, but being more intentional with the wait time. Am I giving students time on purpose to access their IPS, to put stuff in there or to recall it? Because it is deeper in the brain and it isn't auto-recall things, it is time, I have to give time to access. Have you ever been asked something, you're like, wait, give me a minute to just think about this, right? It takes time to think. We want students to be thinking when they're growing their IPS. All right, we're going to stop and give some time to reflect. Is there anything that you would like to add to your essential question? All right, there's a lot of detail in here again, but we're going to think about the power of pictures. When we're learning something, we experience the situation in the world. If I have a mental anchor to hook it to, then it goes into my brain into what's called a scheme or a hook, like water, and that means we're not learning. We're activating a scheme that we already have. We know it's there. We don't always want to be in a state of learning, by the way, right? Sometimes we want to know what schemes are there, and we want to be able to build on those schemes or those hooks for students. So if I'm perceiving a situation, I have a hook to attach it to, then it hooks into a scheme that has already been constructed in my brain. But if I perceive a situation, and I have glasses here to signify perceiving, but it can be with all of my senses. I'm touching things, I'm hearing things, I'm feeling things. If I'm perceiving a situation like this one, and I don't have a hook for it, a great indicator is you'll see the look on somebody's face, which many of you did when I said subluxation or the 1, 2, 4. That is a fancy way of saying disequilibrium or perturbation, but what that really means is Awesome. This is a state of not knowing. That means my student is ready to learn this thing. In order to construct a new hook, not knowing is a necessary condition. That phase has to happen to be able to learn something new. This is the phase that we often rob students of unintentionally as parents and educators. When they get confused, we say they get confused and they don't know, we quickly can come in and say, oh, let me show you. Or look at how Meredith is doing it. Or look at our poster, make it look like the poster. And we can rob them of the opportunity to make sense of it for themselves out of the best of intentions of trying to help them, because it's uncomfortable for us to see them struggle at times. Same thing with parents. Whenever our kiddos are doing homework and they get stuck, they get frustrated, we may say, here, let me show you how I do it. That can rob of this necessary not knowing, because the brain needs to feel this because it doesn't like it and it wants to re-equilibrate. When it re-equilibrates, that's constructing the new hook. Okay. There's a lot of fancy stuff that's going on in that thought bubble that neuroscience and cognitive science has taught us about the brain mechanisms that are happening whenever learning is happening. What we're going to focus on is what do we do to keep students in that thought bubble process to construct new math knowledge. There are 2 3-part things. The first 3-part thing we want to remember whenever we're helping students construct new hooks and learn math conceptually is a concrete, pictorial, abstract progression. So, I need to experience things, touch things, move things, concretely experiencing them. This is where manipulatives come into play. This is where if I'm doing number hops and jumps and building up to negative numbers, which we need to get to by middle school, then I want students actually jumping and moving. PE, whenever we're doing things like hopscotch and number lines and actually putting words to numbers as I'm moving my body, that is helping with that concrete experience of making sense of numbers. There is a myth that concrete experiences are for students that are struggling or for younger kids, and that is false. I have to experience mathematics concretely for every concept that I'm learning. Concepts are big. So if I'm going to be understanding covariational reasoning, which is what's needed for function and calculus, I have to concretely experience things first. So if you hear or have that myth of, well, manipulatives are just for the kids that don't yet have it, sometimes I may have it procedurally, but not conceptually. And so ensuring students have that concrete and pictorial understanding is really important to being mathematically fluent. Then I need opportunities to draw those things that I'm experiencing, to make pictorial representations and use my fingers. Fingers are a part of the pictorial phase. And then I connect those to abstract words, symbols, and numbers. If I'm in abstract words, numbers, and symbols first, or mostly, then I'm going here in the brain, mostly. So what would it look like with multiplicative reasoning? Remember, it's a concept. So this is what I need to have skills. I see lots of questions over here about math skills. Math skills mean I have it constructed conceptually and I have procedural fluency with it. So I have procedural fluency with meaning. Procedural fluency without meaning is memorization. Conceptual understanding without procedural fluency is also not as beneficial for our students, because we want them to be fluent. We want them to have automaticity, but it comes from that conceptual understanding first. So if I am understanding multiplication, or I am helping my students develop an understanding of multiplication skills, they need to have experiences of concretely touching things, like cubes, and putting cubes into towers. Then we can begin to pictorially represent these. And the pictorial, it's not like one concrete experience, one pictorial experience, one abstract experience, right? This is a spectrum of development that builds across grade levels. I'm going to show a connection to Bridges in this in a minute and how Bridges builds this through models, but it's important to remember that it's not concrete, pictorial, abstract every single lesson, every single day. It's part of developing an understanding across the spectrum, and it's a way I want to think about differentiation. Where are my students in their spectrum of learning this concept? Are they beginning at the pictorial phase or more towards the abstract pictorial phase? So they're building to more abstract pictures. Remember, fingers are important. There used to be a myth that if I'm using my fingers, I'm slow or bad in math. That's the part that's connected to the IPS. I want them to use their fingers to be able to represent and make sense. And then if I do things like flashcards, flashcards are going to be in the abstract because they're just numbers, right? If I'm just doing flashcards without ensuring that the students have these things before, then that's an example of going to this point. But I do want them to be fluent in them. So one way that you can modify that slightly is with using things like fluency towers. If they have this extension and connection to towers and cubes, then you can say things like, okay, now we're going to practice. We used to say practice our threes. We may be able to say things like, we're going to practice working with towers that have 3 cubes in each. If I have 5 towers with 3 cubes in each, how many cubes is that? Because this is giving a mental anchor for them to anchor back to. And at first they may record these with pictures. Then they may start recording them with numbers. Then they may start recording them with more fluency because they can work back and forth with the pictures in their head. If I asked you to do your multiplication facts, and I want you to be able to do 20 of these in 1 minute, and if you don't know them, I'm going to do some flashcards with you, with these. Do you have a picture? I just got to memorize them. And so what historically has separated people who identify as strong in math versus not as strong in math can be how well are they at memorizing and handling stress, not so much how well do they know the mathematics. So we want fluency, but we want pictures to make sense of what these are first. Okay? Then we build to building things like 7 towers with 3 cubes in each to make abstract connections. If I get to something like this, do I want them to do this concretely? No. Do I want them to draw every single tower and cube with this? No. This is what I mean by you don't want concrete, pictorial, and abstract in every single lesson. But you want those anchors of those concrete and pictorial experiences to be able to imagine here. So if I am building this, can I imagine that I have built 17 towers? And can I imagine 23 cubes in each tower? But 17 times 23 is not numbers my brain likes. What numbers does it like?
10, 7, 23.
Primary. This is why this is so important whenever you are decomposing numbers, because you're decomposing single units. And you're saying 17 is a thing made up of 10 and 7, or 1 and 16, or all the other ways that we can break it apart and make it, because I've got to be able to get to the point where I can break apart things like towers now to be able to make sense of this. So now I have 10 towers and 7 towers. My numbers should always be labeled. I want students talking about their numbers and what they mean all the time, not just labeling it at the end of a story problem. If I can imagine a tower with 23 cubes, how would I want to break apart or decompose 23 into friendly numbers? 20 and 3, or 10, 10 and 3, or all the different ways I can break it apart, and all would work. But if we get to the point of doing it through tens, what are we building here? I heard it. Area model. Area model is one of the 5 powerful pictures the brain needs
to make sense of 95% of elementary mathematics. There are 5 powerful pictures the brain needs by the end of 5th grade to have access to 95% of middle school math and beyond. So if I don't understand the importance of the pictures, or the why behind this, or that this is a powerful picture, I may be inclined to skip this part of the lesson because I never learned the area model. I know how to multiply with the compact method. That's similar to earlier when I said copy dot flip to just get an answer to a division problem, because I didn't understand that the powerful picture the student needs to be able to continue to build on that in higher level mathematics. So you guys are providing the most important grounding for students' mathematical learning. It's not just about getting answers to addition, subtraction, multiplication, and division problems. It's not just about finding out how many. It's building the picture paths that negative units will attach to, that algebraic units will attach to, that fractional units will attach to. So just briefly, what would I do to get the answer here? 10 times 20, and this would be 200 what? And that's important. Is it 200 towers or is it 200 cubes? Multiplicative reasoning is about coordinating different units together. It's a really important part of the brain exercise to make sense of this. This would be 140 cubes. What do I do once I multiply all these out? Add them. So what? Why does it matter? What we did here was like 10 plus 7 times 20 plus 3. Agree? When I get to middle school, I see things like this, middle school and high school. Do you remember these things? Some of you are like, I remember those. Yeah. There was a trick that we learned to do this. Does anyone remember the trick? FOIL. Yep. FOIL was just a copy dot flip trick. It was multiply these, multiply that. But what I was really doing here, and this is why area model is so important, because it builds to algebraic units in middle school and high school. Was x and 7 positive units, x and 3 negative units. What is it? X squared. 7 units of x is 7x. Negative 3 units of x is negative 3x. And then there's no memorizing, is it a positive or a negative here? This is like 7 towers. And in each tower, there are 3 negative units. How many units is that altogether? And is it 21 negative units or 21 positive units? 21 negative units. We ask kids to memorize so many rules in math. Sometimes the sign is different, sometimes it's the same, sometimes the numerator is different, sometimes it's the same, sometimes I do this butterfly thing, there's so many rules, and that's why I hate math. Also, what we tend to do when we're doing that is tell kids to listen to somebody in a position of power, do what you're told, even if it doesn't make sense. Don't question, don't wonder. The exact opposite of being grounded in equity in math. When I'm saying, follow my rules if you want to be successful. Don't question, don't wonder. Okay. So we want them to question, we want them to wonder, we want them to make sense of, to be able to reason through, not to memorize a whole bunch of rules without meaning. I do this one whenever I'm talking with middle school students, or middle school teachers and high school teachers, because they will say manipulatives are for little kids sometimes, or my kids that are struggling. I also want to address that for a minute. It's not our kids that are struggling, it's students that are earlier in that path. Whatever that brain cognitive path is, they're all somewhere along that path. Our job is to know where they are in that path so we know what they're ready to learn next. Some are earlier, some are further along. Earlier in the path, I may be concretely touching and moving things around, drawing pictures to represent those concrete things, and then describing those with words, symbols, and numbers. Most of us probably experienced equations this way, without pictures or meanings behind it, which also may be, when am I ever going to need this? Why are there X's in here? What does this mean with algebra? Because I haven't connected it to the unknown. All right, pictures with bridges. There's some really good resources that the coaches know about within Bridges to help understand how these pictures develop across units and across grade levels. So if you're like me and we're at the division of fractions unit and you're like, skip that, there's not enough time for that, we have too many things to do, challenge you to stop and think, why this picture? Where does it fit within the spectrum? And then make the decision to use it or not by being an informed consumer of the Bridges resource based on what you know about how math learning happens. So in the primary grades, Bridges does a lot of things with models like this. That is connecting a number with a thing in lots of different ways, through moving on number lines, through beads, through cubes, through tens frames, through all that stuff. That is a foundational importance to being able to build things now like arrays and putting those together with units that then become multiplication equations and division equations. And then the arrays get removed. But if we've had the experience with the tiles and with the towers and with the cubes, then a prompt I can use with students is, what would be here if we drew it? Or what items would be here? Because I don't want students drawing every single problem all the time. That's part of the learning process. I want them to get to this point where they have procedural fluency and be able to imagine. Can you imagine 12 tiles in here? Can you imagine this as an array with 12 tiles that has a side 3? So what would go up here then? How would I know? So now the division symbolism starts to have meaning to it with picture and concrete experiences that I've had. Or what items would be here? Because I don't want students drawing every single problem all the time. That's part of the learning process. I want them to get to this point where they have procedural fluency and be able to imagine. Can you imagine 12 tiles in here? Can you imagine this as an array with 12 tiles that has a side 3? So what would go up here then? How would I know? So now the division symbolism starts to have meaning to it with picture and concrete experiences that I've had. What do you think the greatest predictor of students' math achievement on standardized tests is by the age of 6?
Knowing that picture model?
Someone's using context clues. Has something to do with pictures, right? Yeah. And do you remember what I said is an important part of the pictorial phase? I'm going to lose these, so remind me when I'm looking all over. They're right there. Thanks. Yep. Fingers. So students' ability, it's called finger dexterity, to manipulate and coordinate their fingers is the greatest indicator of their math achievement per standardized test. So there are things that you can do like number mazes, where they have like a blue dot, a purple dot, a red dot, a green dot, and then there's mazes and they have to follow the maze with their fingers. This is why it's important to be grounded in how math learning happens, because if an administrator or somebody comes in and they're like, why are they doing these things with their fingers on, it's supposed to be math time, let's get some math stuff out. You can say this is growing their math brain because it's finger dexterity that's growing the IPS so that they can have anchors in here to attach the abstract numbers to. Moving things like blocks, I already talked about that. Building stuff, that is helping building the visual spatial that connects to the IPS as well. Anything I can do to move my fingers and body by the age of 6, and of course it's beneficial as we move on, but this is one of the research pieces. So what about by age 13? Do you think it has something to do with pictures, Mark? It does, yes, the power of pictures. So one of the research things that I showed you that had a publication date of 2021, that's this piece. Prior to that research coming out, the greatest predictor of a student's achievement was socioeconomic status. And we can guess why that is, right? Because it's wrapped up in a whole lot of societal structures, language, and the way we test, and all of those things that we can talk about in another day. But all of that can be superseded by this thing. So this is something we can do in our classrooms to help support students' math achievement when those bigger things may be out of our control. and that is, what are these? They're pictures. They're specific pictures. Do they look familiar? If you do number talks, there is a strand of these in number talks. Sometimes they are called dot cards, right? The important piece of these is not that I find the total by counting by one. So sometimes when we're doing a dot card, we may think that we want them to see how many are here and tell us how many there are. And then we check it by saying things like, okay, everybody, let's count together. In base 10, it would look like this. Everyone count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 dots here. That's helping them get an answer to this problem. They're telling us how many dots are there. But that's not the goal of a dot card. A dot card is to help them create visual pictures to move things around in their head. It's building those anchors that the other things are going to build on. So when I do a dot number talk, I show it, cover it, and then I say, what did you see? How did you see? How many are there? And when somebody says, well, I saw these two, and then these two, and that made 4, and then I saw these 2 and these 4, and I put those together, now I'm attaching pictorial to abstract. And I can also use questioning like, you didn't have to count everyone? You just saw 2? That's really cool. Kate, you just saw 4 without counting them? You can just see that? That's really cool. And then my questioning there is helping other students be prompted to, I don't have to count every single one. I can start to see things in groups and manipulate and move them and hold them in my head. That's the power of dot card number talks. It's also building what we now know that by age 13, this is called subitizing when it's younger. I can subitize or subitize up to 5 things at a time. It's pronounced both ways. So in primary, we talk a lot about subitizing and subitizing. But intermediate and middle school and high school, it's also important to continue these, and it's called groupatizing. So I'm grouping smaller things that I'm chunking and holding together. It's like an analytical mental aerobic for here. Students that have stronger groupatizing counter and outdo and overcome the SES, the socioeconomic research that existed before.
Brains want to learn. Students want to learn. All brains, all students are capable of thinking about mathematics, high-level mathematics, deeply and powerfully. If we skip those concrete and pictorial experiences somewhere along the way, we go to abstract too quickly, or we stay in abstract most of the time, results in pictures like this. Students doing their best to tread water, keep their head above water, but they may drown at 3rd grade, or fractions, or Algebra 1, or calculus, or university engineering. How does the brain learn math? What would you like to add to your essential question? We've thought a lot today about how the brain learns math. You may have more questions than answers at the end of this, and that excites me. The intent of this module was not for you to leave with a nice, neat package of, okay, tomorrow I'm going to go in and do this. It was to prompt your thinking, prompt your wondering. What are some things that I experienced myself as a student in math classes that were in alignment with or not in alignment with how the brain learns math? What were some things that I was taught to do to support math learning that was in alignment or not in alignment with math? What are some things I learned today that I may want to share with a colleague or share with parents or implement in something I want to try to really center and think on? So take some time. You can use the QR or the bit.ly to share your thoughts around what you're currently thinking in connection to how does the brain learn math? What does that mean for you?